So today's lesson is the second one in this unit on periodic functions and trigonometry. We're going to look at how we measure angles and something called the unit circle. So we're going to work with angles in what we call standard position. Standard position refers to the manner in which we measure their angle. We're going to find the coordinates of points that fall on this thing called the unit circle. And then from that, we will be able to determine exact values for sine, cosine, and tangent functions for some particular angles. So first, what do we mean by an angle in standard position? The angle in standard position is when the vertex is at the origin. So the vertex is where the two rays, right, intersect. And one of those rays is on the positive x-axis, and the other ray is what we measure to. So you can see here by this diagram. So here's our vertex. Right? The initial side of the angle is on the x-axis, and we call it the terminal side. You could think of it as where the angle measurement ends. So terminal means end here. So this is how we will be measuring our angles as we work further in this unit. So let's look at some examples, right? This angle right here would be 90 degrees. Now I'm going to use this letter theta. It's the Greek letter. It looks like an O with a line through the middle of it, but it's a very common mathematical symbol to represent an angle measurement or angle value. So we have 90 degrees. We went to the opposite direction. That gives us 180 degrees. If we go 3/4 of the way around the circle, right, that gives us 270 degrees. And if we go completely around the circle, as you know, that is 360 degrees. Okay, so these are kind of four common angles that we can measure using this concept of a standard position. Now let's look at one other example. How would we define this angle here? Well, we would have to know first what this angle is from the x-axis, right? So if I told you that was 30 degrees, then we would add the 180, right, plus the 30 to give us 210 degrees. Now, when we go counterclockwise around the circle, that gives us a positive angle. So we always start at the positive x-axis, and then we move up through quadrant 1, then 2, then 3, then 4, okay? But we can also define the angle by moving it clockwise, in other words, through quadrant 4, then 3, then 2, then 1. And in that case, we would have a negative angle when we measure it in that direction. Now, let's jump back to geometry here for a minute. We're going to look at some what we call standard angles. And these standard angles come from two common triangles. One is a 45, 45, 90 right triangle. The other is a 30, 60, 90 right triangle. And in both of these cases, we are going to define the length of the hypotenuse as one unit of length for the hypotenuse in both cases. So if we define the hypotenuse as 1, we can then determine what the lengths of the sides would be using the Pythagorean theorem. Right? So if we have our 45, 45, 90, right, we know the two legs have to be equivalent. And so those two legs would be each length of 1 over the square root of 2. And as you can see below here, if we use Pythagorean theorem and square those, we wind up with 1, right? The square of the sides, the sum of the square of the sides equals the square of the hypotenuse. And then similar for the 30, 60, 90. We have a hypotenuse of 1. The short leg will be 1/2 of that value, so 1/2. And the long leg will be square root of 3 over 2. So keep those values in mind. You're going to see them show up here again in a minute. Now let's review the sine, cosine, and tangent as trig functions of an angle in a right triangle, right? So Again, we'll define these as the hypotenuse, and then the sides we're going to define as first the adjacent, which is next to the angle of interest, and then the opposite, which by its name is the opposite side of the triangle from the angle of interest. So here are the definitions of sine. Sine is equal to the opposite length over the hypotenuse, right? So opposite over hypotenuse. Cosine is equal to the adjacent over the hypotenuse, and tangent is equal to the opposite over the adjacent. So if you might remember from geometry or your math 2 class, SOHCAHTOA, right, is a way to kind of remember these functions for sine, cosine, and tangent. Now, let's talk about the unit circle. The unit circle is just what it sounds like. It's a circle that we draw onto an XY coordinate system where the radius of the circle is equal to 1 unit. And so if we scribe, right, that radius around with one end at the origin and one end at the end of that unit length of 1, we create a unit circle. It would have a radius of 1 or a diameter of 2. Now, what we're going to do is take these 2 cases of right triangles, 30, 60, 90, and 45, 45, 90, and fit them into our unit circle. So here's the 30, 60, 90. Notice remember we said the hypotenuse of our right triangle was going to be a unit of 1. So that hypotenuse basically becomes our radius, right? Has a length of 1. And what we now want to do is say, okay, if we had that angle, right, measured from the positive x-axis, what would be the coordinates of that point of the triangle that lies on our unit circle? So the x-axis, right, is going to basically be the short leg of the triangle. So that would be 1/2. And the long leg of the triangle will be square root of 3 over 2. Right? So we could write the coordinates for that point, right? The x coordinate would be the long leg, square root of 3 over 2, and the y coordinate would be the length of the short leg, 1/2. Now, what if I ask you the question, what is the sine of 30 degrees in the unit circle? Remember, sine is opposite over hypotenuse. So we want to find the opposite length. Now, the opposite length will be the short side. Notice the hypotenuse in every one of these cases will be equal to 1, right? By definition, the hypotenuse will always be the radius of 1. So we really just need to concern ourselves with the y value. And the y value in this case, right, is 1/2. So 1/2 divided by 1 is simply 1/2. So sine of 30 degrees is 1/2. What about the cosine? Well, same thing, except now adjacent, right? So we're going to take the x coordinate value and divide it by 1. So that's going to be square root of 3 over 1 divided by 2, or simply square root of 3 over 2. Now, what about tangent? Tangent is opposite over adjacent. So this time it's going to be the y coordinate, right, divided by the x coordinate. So let's plug those in. Going to be a little messy, right? We've got a complex fraction, 1/2 divided by square root of 3 over 2. And to simplify this, right, we multiply by the reciprocal. So if we do that, the 2's will divide out and we're left with 1 over the square root of 3. All right, so oops, let me back up here. So this is how we will find the cosine, sine, or tangent for any of these standard angles inside the unit circle. We could do the same thing for 45 degrees. Okay. All right. So a couple last concepts here. How do we measure angles using something called a radian? Okay. We've used degrees, right? We know there's 360 degrees in a circle. But what about a radian? What does that equate to? And here's how we're going to define radian. When the angle, so our angle theta here shown in red, when it intercepts an arc length equal to the radius, the angle has a measure of 1 radian. Okay. So in other words, if our radius is 1 and the length of the arc is equivalent to that, right? It kind of looks like maybe an equilateral triangle, but it's really not, right? Because one side is an arc. But the angle whose arc is equal to the radius, that is an angle of 1 radian. That's how we define a radian. Now, how many radians equal 360 degrees? Well, we know the circumference of the circle is 2 pi r, right? That would be the total arc length, 2 pi times the radius. But 1 radian is equal to the arc length of r, right? R is being our radius. So if we want to know the number of radians that's in a full circle, we're going to take our total circumference, 2 pi r, and divide that by r, and we get 2 pi. So the number of radians in a full circle, 360 degrees, we measure the angle that goes all the way around and then comes back to the x-axis, is 2 pi. 2 pi radians in a full circle. Now, we can label some of the axes here as far as what their radian measurement is. And the reason we're talking about radians is that in trig going forward, we're often going to work with radians rather than degrees when we're talking about the measurement of the angle. So if 2 pi is all the way around, then 1/4 of that would be pi over 2. And if we went halfway around the circle, that would be pi. And 3/4 of the way around the circle would be 3 pi over 2. And then, of course, all the way around the circle is 2 pi. All right, so last thing is, what if we wanted to convert from degrees to radians? So we have 135 degrees, right? How many radians would that be? Well, we're going to multiply by a conversion factor. So we're going to take our 135 degree measurement, and we know that we can multiply that by a conversion factor. 2 pi radians is equivalent to 360 degrees. So when we do that, right, we can simplify our degrees. 135 divided by 360, right? We can divide both of those by 45, so we get 3 over 8. And then we get 6 pi over 8. Now we can simplify that a little more, and we get 3 pi over 4. So 135 degrees is equal to 3 pi over 4 radians. Let's try one more, 210. So again, we multiply it by this conversion factor, 2 pi over 360. So here, right, we can divide both the 210 and the 360 by 30. So we get 7 and 12, and then 14 pi over 2, but let's divide by 2. So we wind up with 7 pi over 6. That would be 210 degrees, 7 pi over 6 radians. Now, what if we want to go the other direction? What if I know I have 7 pi over 8 radians, 7/8 of a radian, or 7/8 pi of a radian? How would I convert that to degrees? So we're going to do the same conversion factor, but this time we're going to flip it around, right? Because we want the pi, the radians measurement, to cancel out and leave us with degrees. So we just need to simplify, right? We can divide out the pi. What else can we do? Well, we could just go ahead and multiply, right? This is where we grab our calculator. So we get 2,520 over 16, but if we use our calculator to do that, we see we come up with an angle of about 157.5 degrees. So 7/8 pi, remember, is a little less than a full pi, so that's going to be a little less than 180 degrees. All right, so that's the lesson for today. You know how to define angles in their standard position, measuring from the x-axis in the counterclockwise direction. That gives us a positive angle. We know how to find the coordinates of points on the unit circle using our two triangles, right? A 30, 60, 90 or a 45, 45, 90. Those are the common special angles that we'll be working with here in this unit. And then we know how to use the functions of sine, cosine, and tangent to find their value for special angles. And when we say exact values, we're going to leave our answer as a fraction or as a radical, right? If we have a square root of 3 or square root of 2 in our answer, we leave it that way. We're not going to use a calculator to come out with a decimal equivalent. All right, that's it. Take a look at the assignment.